Here we have a rare creature in its natural habitat, the translational scientist. This is Ivan. Brilliant, skeptical, and heavily caffeinated. And a new mission is on the table again. Most cancer patients get hit with combinations of cytotoxic drugs because, when in doubt, just throw more at it. But these days, with antibody-drug conjugates, we're packing multiple fighter compounds onto a single molecule. But let's start pipetting. 1 antibody, 2, sometimes more payloads, all fighting cancer together. Sounds great, right? Now try figuring out the right mix, the synergy, the ratio, the science. Every little tweak changes everything. So we end up running grid after grid of tests just to find that perfect combination. And let's be honest, it's time-hungry and burns through way more samples and budget than anyone wants to admit. That golden synergy we find in the dish? Half the time it disappears when we put it in actual living models. Suddenly, too little gets to the tumor, or too much goes toxic and the magic's gone. To make it worse, unless you nail the exact target expression in your models, none of it matters for translation to real, live patients. Thanks to his elevated intelligence, this remarkable inhabitant is highly adaptive to new challenges. Watch as he searches for a fresh hunting territory, a true apex predator in his loyal companion, Ori. Let's virtualize biological experiments.
We will spend the next 2 weeks on measuring my new ADCs. I hope it works because the company doesn't have money for another test. Oh, wait. I could simulate all experiments needed and it would only take 2 hours. Here we simulated cancer cell lines from the lung cancer lineage. In this indication, there is already an antibody-drug conjugate out on the market. Here, we would like to check if we can find synergy between the DXD ADC payload and some other putative payloads, testing all our hypotheses on a single platform before going to the wet lab. Simulations like this help design the right experiments, faster, cheaper, and with higher chances of success. They let us predict beyond the data we already have and understand what actually drives the biology. We can see here the distribution of HSA synergy scores between DXD and all the further tested compounds. We can see many compounds with relatively higher synergy, especially sirolimus. We want to test some of these combinations further. Since MET has been proven to be a good antibody target in this indication, let's check which of our compounds have higher synergy, specifically in those cell lines that express MET to a higher extent. As we can see in case of sirolimus, the median synergy is higher. We can see the same synergy in the high MET expressing cell lines in the case of mertensine, MMAE, and docetaxel, while we see strong antagonism in the case of etoposide. But it still matters in which dose the compounds can reach this synergy score. If we select specifically some MET high cell lines, like NCIH2085, and look at the synergy heat map across the full dose grid of DXD and sirolimus, we can identify the dose range where we can find higher synergy. This concentration can be reached in the direct proximity of the cells, where the ADC can release the payloads.
And that's it. We've got our selected combination, which means a much higher chance it will actually succeed in the wet lab. If you only take the right experiments forward, you save time, money, and increase the odds that what works here truly translates to the clinic. In the end, it's the scientist, the virtual, and the wet labs together that make drug discovery much more efficient.